Hey students, let me try a video solution here again. This is our last chapter here of the semester. It is from chapter 34 and it's the first one. And part of it is a pretty straightforward problem, but another part of it which makes it a little challenging is the new terms, the new meaning, the new vocabulary. And so if you remember in the lecture, we said that way back in chapter 30, we learned Ampere's law. We learned that the first way of making a magnetic field is from a current, and this would be the current that goes inside of a closed Amperean loop. And so the magnetic field added up over the loop is equal to the current, and I'm going to say conventional current, that goes through that loop. And it was Maxwell who was looking at this problem in terms of a capacitor and was bothered. And so if I put a capacitor, maybe somewhere in the circuit, a resistor, and so here's V, here's C, here's R, we learned there would be a current, and then of course this goes way back to, I guess, chapter 28. It would be the initial current, which would be V over R, and then E to the minus T, and then the time constant, which in this case the time constant is an RC time constant, because this is an RC circuit. Okay. But at some moment, there would be some current, which, of course, would decay away. But whatever that current is at the moment, and according to this problem, it says a 0.1 amp current. Okay, so at that moment, if we did a Amperean loop around here, we would have a current and then a magnetic field, and same thing here, same thing here. And then we get to this little break where there is no wire. There is no current through this Amperean loop. And that logic would say no current, no field. And so would that really be the physical world where there'd be a field, a field, a field, a field, a field? Then it's gone, and then a field, a field, a field, a field. And that bothered Maxwell. In fact, as we were showing in the first diagram of chapter 34, if you did an Amperean loop and did a flat surface, you would get current through it. But if you did a bowed surface, where the surface went through the center of the two plates, you would get no current. And so one surface, which our book called S1, and the other surface, S2, one would say you'd get a magnetic field, and the other one would say you wouldn't. But the whole point of section 1 of chapter 34 is to say this is troublesome. This can't possibly be true. And so Maxwell goes to answer it by saying there's got to be something equivalent to the current. It's not really a current, so he uses an old-fashioned word for a missing current called displacement current. And he hypothesizes that Ampere's law has a missing term. And so he adds that to the equation and begins to study this and realizes that through this area you don't have a conventional current, but you have a changing magnetic flux. And so this right here must somehow be related to a changing flux. And sure enough, his logic is that if you did this loop and you did the flat surface, which we called surface number 1, you would get the conventional currents. And then if you did the bowed surface, you would have surface number 2. And what would go through surface number 2 would be the displacement current, but no conventional current. And so his argument was that the conventional current would have to be equal to the displacement current for this to work, because when you're looking at surface 1, you get this term and the second one 0, But when you are looking at surface 2, you get the displacement current, but you get conventional current as 0. For this problem, if you remember all that from the lecture, and so forgive the wordy mini lecture here, but if you take that little mini lecture, we can actually answer B right away. It says the displacement current. Well, that's easy. The displacement current is the same as the conventional current, which is just 0.1. Ta-da! So B is very, very simple. They've almost given to you straight up. They've given you conventional current, and Maxwell's thinking is that displacement current, the missing current, has to be equal to the real conventional current. All right. So there is the easiest part of it. Now, the changing electrical flux, we could then go to how he then works out displacement current, which it would then be a epsilon naught times the change of the electrical flux. And if you let me do a little mini lecture again, he kind of argues it this way, that the conventional current, I conventional, is dq dt, and then the Q, as it flows through the wire, would also be the Q that goes on the capacitor. So thinking about the Q and changing Q that goes on the capacitor, we could write as capacitance times voltage. And then thinking of a parallel plate capacitor, this is the equation for the capacitance of a parallel plate. And then voltage for a parallel plate, because it's uniform, is just the electric field times the distance. The two distance cancels off. If we regroup area with electric field, that is flux. And so again, at the risk of saying too much, this is his definition of displacement current. So you could do this one pretty straightforward by then saying, okay, displacement current divided by permittivity, free space, would then be equal to the rate of change of the electrical flux. And that's what we're asked to solve for in A. Where's A here? The plate separation, blah, blah, blah. Find A, the time rate of change of the electrical flux. And so it would be just simply this, let me put it down here, the displacement current, which answering B is the same as the conventional current, divided by the 8.85 times 10 to the minus 12. So that would be 0.1 divided by 8.85 times 10 to the negative 12, and coming up with 1.13 times 10 to the 10th. Yay! And I suppose I should be careful with my units. Flux would be electric field. Where'd it go here? Electric field times area. So electric field would be newtons per coulomb, and then square meter. There's the flux. And then divide by time. So it would be a newton times a square meter divided by coulombs times a second. All right. Hope that was helpful. Now, there's other ways we could do this that would make it much harder. We could actually dive into the dimensions as they give us and then actually use these and find capacitance and all that. But that would be longer. And I think kind of missing what the whole point of section one was about, and Maxwell's kind of thinking of him adding to Ampere's law. So now we call this the Ampere-Maxwell equation. And it lists the two ways of making a magnetic field, either conventional current or a changing electric field. All right, take care.